Hello and welcome to this demonstration. We're going to take a closer look at IBM Cloud Pak for Integration, which runs on top of Red Hat OpenShift. We're going to look at different integration scenarios, and the demonstrations will use a dashboard so you can see exactly how the traffic behaves when we add things, take away things from the architecture. So we will show you resiliency, how that works, scalability and extensibility in the platform. So let's take a closer look at the initial setup that we're using. So first off, what we have for the setup is a GitHub repository, which the pipelines in OpenShift uses to initiate the whole demo and the whole architecture. We have a program that emulates 250 mobile apps initially. So the apps send in traffic to the integration layer, and from the integration layer we send it into the IBM MQ messaging servers, and we have a backend, a core banking application. So the demo uses a dashboard to show exactly what's going on when it comes to the traffic. So we get metrics from all the different layers. So every 3 seconds we get metrics on what's going on. So here's the dashboard ticking away live. We have some buttons that actually triggers the build pipelines so we can change the architecture. We will use that in the demo. And here we see the mobile app ticking away at 250 requests per second. But let's dive into it. First demo is that we're gonna take down one of the integration servers. And the way we do that, we copy the name of the middle one here. Then we go into OpenShift and we actually terminate this integration server. This to simulate let's say we're taking down a server for maintenance, or it could also be a simulation of a crash. Let's say one of the integration server goes down in a hardware crash, for example. So we delete the pod. The pod is where the runtime for this particular integration server is running. So we simply terminate it. And let's go back to the dashboard to see what happens. So of course the traffic goes down to 0. And now we only have 2 integration servers. OpenShift and Kubernetes in general have the ability to have state. So in this case we have configured the state to Kubernetes OpenShift to always have 3 integration servers. So OpenShift is working in the background now to get the server that is down to restart that as soon as possible. In the meantime, the other 2 servers are handling the traffic. So here we see after a couple of seconds, the middle server comes up. But the major point I'm making here is if you look at the mobile app traffic, that is basically flatline, right? So if you were an end user with a mobile app, you wouldn't notice anything, no disruption whatsoever for a server going down, planned or unplanned. Let's see the same or similar case when it comes to MQ. In this case, we're gonna do the same thing with an active MQ in a native HA setup. So we copy the name and we go back to OpenShift. And in here we do a search. And here we actually get 3 pods because we have 1 active, if you remember the picture from before, and 2 replicas. So we have 1 who's actually handling the traffic at the moment. So let's see what happens if we terminate that one. So if we delete that pod, what will happen in like 2 seconds? MQ-1 takes over the traffic. So let's see what happened in the dashboard. We can see a bump in the road there when the active server went down, but immediately a passive one takes over. And the major point again is the mobile apps just keep on ticking with a flat line, so a mobile app user wouldn't notice anything in this case. So let's take a look at the third demo. Here we're looking at MQ streaming queues, and we're also going to upgrade the whole MQ cluster in one go. The way we do this is by using a different branch up on GitHub and the build pipelines, if you remember. But first off, what is MQ streaming queues? Let's say we have a queue and the consuming app to the right. When it consumes the messages, they're gone from the queue, right? So an MQ streaming queue is a copy of the original queue, but the original flow is completely unchanged, right? So what we then can use the MQ streaming queue for are different use cases. Maybe we want to store an audit trail of messages, we want to, or maybe stream it out somewhere, or use it for analytical purposes. The most classical use case I've seen is to use it with Kafka. So IBM MQ is perfect for one-time transaction, and Kafka for more event-based type of use cases. So the way in the demo we're going to use the streaming queue is to use this notification service. When we press deploy here, we will actually trigger the build pipeline to use a new branch, the notification branch that we're looking at right here. So what the new branch includes is an alter statement. So we make a streaming queue from an existing queue. What we'll also do in the same go is to upgrade the MQ clusters. So we can go in and look at one of the configurations here. It will be upgraded to this new version, and that will be done in a rolling fashion, so traffic will still be able to go through this whole architecture. So we press deploy, and what happens here is the pipeline gets triggered, then it goes up to GitHub and uses the new branch that we took a look at. So this is a quick view just in OpenShift where the pipeline is running, and that is reflected in the dashboard. So now it's upgrading the first pod, the second pod, the third pod, and so on. I speeded up the clip here so we're not watching paint dry, but what we can see is that the traffic is ongoing right through the MQ layer. So once again, the mobile apps won't notice anything. And finally, we see the notification server start receiving messages from the new streaming queue. Okay, last step that I want to show you is around scalability. So the way we show this is in the dashboard again. We press scale, and what that does is kick off another build pipeline inside OpenShift. Inside OpenShift, we now have a pipeline that will install a new MQ cluster and a new integration server. So here we can see the logs inside the pipeline starting to provision a MQ cluster with native HA, and it will join the other two in a so-called uniform cluster. I speed up the clip here, but there we see it's up and running and starting to receive messages to handle potentially a larger load into this infrastructure. Also in the pipeline, we will scale, so we add a new integration server that will join the other three and start to handle the load from the mobile apps. And there we see that one coming up, starting to balance itself out. But then we can press the Request Plus button here in our demo dashboard to increase the load, just to see what happens. So here we can see the load starting to increase. When it comes to the mobile apps, they go up to 350 concurrent mobile apps being emulated. So what we can see is both the integration layer and the messaging layer balance themselves out so they can handle the new load. The new load could be, let's say we have an increase in sale around Christmas, for example, and we quickly want to be able to extend the architecture. So that's it for the demos in this clip. If you remember, initially we had this setup for the demo. We had 250 mobile apps, 3 integration servers, and 2 active MQ servers. And we extended the whole architecture throughout the demos, so we ended up with this picture. So we increased the load to 350 mobile apps, concurrently sending in requests to the integration layer that was extended with 1 extra integration server. We also added a new native HA cluster with an active MQ server, which joined a so-called uniform cluster. We also created a streaming queue from an existing original queue within IBM MQ. And we saw that in the demo dashboard, receiving notifications. So that's it for this short demo. I hope you found it interesting, and see you next time.